All right, guys, welcome to EE222. We are on, let's just flip the document camera. We are on, and are you able to see that? Or is it too dark? Is it fine? We are on week, what is this? 5? Lecture 2, and today's date is it the 20th? All right, we now move on to a new topic. Hey, is that visible? Hang on. Should I turn on the lights? Is that better? Okay. All right. Okay, we are now at a new topic. Let me switch back to the document, to the PC. In fact, what I've come to realize is that today is Wednesday, right? Wednesday. I don't think there are any students in the region. There are no students who are stuck in the region because nobody's been, I've been emailing on multiple occasions with regards to if you are in the region. You may have received this message from me that if you're in the region, please contact me urgently. And nobody's been responding. So I'm assuming that everybody's in Fiji. Everybody is here at Lozala. All right. I might stop using Zoom. And just tell everybody just to come to the campus. Right. Or if you've got a real problem, then you can have a delayed coverage of the lecture, because I still believe that even though sometimes I don't use Zoom, you will still see the lecture recordings. Yeah, you are able to still access the lecture recordings, but it's delayed by 1 or 2 days. Am I correct over there? Okay, all right. Okay. All right, guys. So we are on week 5. And I think some students were asking for an extension. For some reason, they were, some students were not able to upload their lab reports. Is that correct? Yeah, okay, all right. So I'll extend it. I'll extend it till tomorrow morning for those set of students, right? Because this is well and truly should have been over by now. And today is the 20th. And we'll allow it till tomorrow. Okay? So I think you should, I guess, just check on your mobile phone if you're able to access the lab 1 assignment box. The due date is something else, and the other due date is 26th April. I think that's fine, right? That's this week because, well, some of you will be doing the lab on 22nd, Friday 22nd, yeah? And I've given you time till, okay, I can extend that till 26th or 27th, but right now it says 26th, right? Okay. All right. Okay. Yeah, it seems that I'm the only person who is on Zoom right now, and maybe yeah, it seems there is absolutely no point in us running this lecture on Zoom as well as on lecture recording as well as live over here. So this might be one of the last lectures to be done on Zoom. All right, let us now move to a new topic. All right. Okay. So let us see. Let us have a look at what was also on the Moodle shell, and if there's anything which is missing. So let's have a look at this. Right. We've done all of these laws. I've gone into the details. I've proven those laws. Yeah. Okay. That's very straightforward. There's some examples here. Okay. We're going to talk about sum of products and product of sums. There's all these gates. We've spoken about all of these gates, right? We've spoken about all of these gates. Hey, and these are some of the, remember sometimes I say, hey, I've given you a homework problem. Remember, this is the homework problem. No gate. Yeah, we've done all of these gates, the timing diagrams as well, right? Sometimes I may have not done the timing diagrams, but I'm expecting you to do it in your free time. Then there's some theorems. Remember, we spoke about what do you call, when we break the bar and we change the sign. When you break the bar and you change the sign, what do you call the theorem, guys? It should be on your fingertips now. De Morgan's theorem. Yes, De Morgan's theorem. Right? Okay. So these are all have been covered. Oh, by the way, there we go. NAND gate. We did this yesterday. So most of this stuff, I could have just simply projected it to you via the Moodle shell, but I wanted to show you the derivation of how we got there, right? Okay, it's important how you understand. So we did all of this yesterday. And then now there's some exercises over here. So my point this afternoon is that sometimes not sometimes, all the time, you've got to look at both. You've got to look at what we have on the Moodle shell and what we're doing in class as well. In class, what I'm doing is actually I'm supplementing. This is your main notes. Your main notes is on the Moodle shell, and I'm supplementing. I'm giving you extra example. I'm giving you the proofs. So if you go back to our theorems over here, what I did was I went and did a proof of all of these theorems, right? Consensus and consensus and all that sort of thing. I did a proof, okay? All right. All right. Now, today's lecture is about something called sum of products and product of sums, right? Okay, so the point I want to make now is that you have a number of ways of describing circuits. Firstly, you can draw the circuit diagram, right? A Boolean, a digital circuit. When we talk about circuit over here, we're obviously talking about digital circuits or digital logic circuits or binary circuit. So you can draw the circuit diagram. What's another way of describing the behavior? If you want to talk about a circuit, you can draw what? You can draw the truth table, right? Another way. What's another way? We can talk about the same thing. Yeah, you can write the Boolean equation. You can write the Boolean algebraic equation, right? So these are three ways we have learned so far. And they all refer to the same thing. What's another way which we have sort of touched on, but I didn't draw in each and every round because it was too time consuming. What's another way? There's another drawing which is important, but I didn't draw it. Another one. Somebody said it. Timing diagram, right? It's there. It is part of your syllabus. You've got to know how to draw a timing diagram. But I drew one or two, but I didn't draw all of them because I said, hey, it's going to take too much time in the lecture. So when you look at a truth table, or you look at the circuit diagram, or the Boolean algebra, or the timing diagram, they're all the same way, all different ways of describing the same system. You may have one system, but different ways of drawing it, right? So just like when you were in secondary school and somebody drew you a box, you can either draw the box in isometric, or you can draw it in oblique, or first angle projection in orthographic, third angle projection in orthographic, or there was single perspective point of projection, or dual point of projection, or there might be some other way of writing out the coordinates and so forth. But they're all talking about the same block, right? Yeah, but different ways of drawing it. Same thing goes over here. There may be the same system, maybe a security system, maybe a PIN number system for your mobile phone. Like how we have 4 PIN numbers to enter your mobile phone. There may be one method maybe to draw the truth table, another method maybe to draw the circuit diagram itself, another method to write the Boolean expression, another method to draw the timing diagram. Now, I want to now introduce you 2 more methods. So we've done 4. Which 4 have we done? We've done truth tables, you know that. We've done Boolean expressions, you know that. We've done circuit diagrams, you've already done that. We've done timing diagrams, we've done that, right? Now I want to introduce you 2 more. Sum of products and product of sums. All right. Okay. Now, let's now, so over here, today's lecture, I'll give you mostly from this, and certain things I'll write down, you know, whatever needs emphasis. Okay. Now, this is a Boolean expression. This is a Boolean expression, right? Now, let me give you some definitions. This here, okay, now what can you tell me about this Boolean expression? This Boolean expression is, all these are what? A, B, and C. What can you tell me about the relationship between A, B, and C? How are they plugging in together? They are ANDed together, right? They are through an AND gate. So that's an AND gate, that's an AND gate, that's an AND gate. How are these three AND gates plugged in together further? Through an OR gate. Okay? So remember that. These are all AND gates, and they are plugged in via an OR gate. Okay? Now, we call this one AND gate a minterm. In this particular style, just like when you, I hope some of you did some drawing, because it's a very good way to describe it. Just like when we do truth table, there's a particular way we draw the truth table. Yeah? Whenever we talk about a truth table, there's a particular standard. There's a particular standard. There's a particular style we draw the truth table. Can you see? There's a particular way we write the truth table. Right? You can't just go and draw any table and then just draw the truth table. I'll tell you a funny story. Is that in one of the years when I was teaching this course, I've taught this course on and off for a long time. I asked the student to draw a digital signal over a bus or a wire. And the student drew a bus, actually drew a bus. Right? Okay, and a bus stands for, a bus means multiple lines going in parallel. When you have multiple wires, like say 8 wires going in parallel, that's a bus. When you have a single wire, it's just called a wire, right? Or a line. When you have multiple lines, it's called a bus. But the student drew a bus, all right? Okay, and similarly, I think the student was making a joke, or I don't know whether he had attended any course. When I asked, this is another student, another year, when I said truth table, he drew a table, like a table, of a dining table, right? So what I want to tell you over here is that some of these words over here, they may seem like normal everyday words, but they have a technical meaning in our particular case, right? Okay, now just like truth table, we have a particular formatting. When we talk about sum of products, there is a particular formatting. That's the first point I want to make. The first point I want to make is that sum of products will always be and then all these end are ORed together. That is the formatting. That is the format of sum of products. Just like when you had orthographic, if somebody said first angle projection, what is it? First angle, the plane is at the bottom or is it at the top? The plane comes on the top, right? That's a particular format, right? Third angle projection, the plane comes at the bottom, all right? Okay? Or the other way around. Yeah, okay. Right. But there is a particular, my point here is there's a particular format which you've got to follow, right? So for sum of products, your AND gates come first, and then they get ORed together. The output from the AND gates get ORed together. Now each of these AND gates is called a minterm. It's called a minterm. This is all on Moodle, all right? And each of those inputs into the AND gate is called a literal. All right? Each of those inputs into those AND gate is called a literal. All right? Okay. Now, okay. Now, in this sum of products, what they tried to do is they tried to make it easier for us to understand. They tried to call the terminology, right? They tried to rename some of the terminology in order to make it easier for us to read. So if you look at AND gates, so if we put a proper name to this in terms of, this is OR of AND, right? Okay? OR of AND. What are we doing? We're taking all these AND gates. The output from each of those AND gates is being ORed. Let me show you a diagram of this. Not of this circuit, but a sum of products circuit. Sum of products circuit. Let's have a look. There we go. Have a look at this. Look at this. This is not the same circuit from last time, from that one there. Can you see it's AND gates? First layer. Second layer is an OR gate. So one way to name this type of circuit is it's an OR of AND. But when you read it in English, it's an OR of AND. It sounds very confusing, right? It's an AND of or it's an OR of AND. It sounds very confusing in the English language. So what we did was, okay, and this is another one. This is AND of OR, okay? All right. So here's another one. This is an OR of AND, okay? This is an OR of AND. Now, what that basically meant was, where did it go? All right, here we are. So basically, calling this an OR of AND sounds very confusing. So what we did was, if you look at this, in terms of mathematics, let's flip back to mathematics, only for naming purposes, we call this AND gate a sum. Yeah? We call this AND gate a product. This is a product of A, B, and C. This is a product of C, B, and E. This is a product of B bar, C, and D bar. Right? Okay, but we know that when we talk about product, it's a sum. Right? Just for the purpose of naming. Right? In this particular convention. Remember, truth table is another system. Timing diagram is another system. Drawing the circuit diagram is another system. Writing the Boolean expression is another system. This is another system, sum of product. So in this system, we call this a product. We call all these AND gates a product. And we call the OR gate a sum. Yeah, we're just calling it. It's only the naming convention in this system. In this system. Right? So in the end, this becomes a sum of products. Right? This becomes a sum of products. Now, let's now take it to another level. Right, now, in the standard sum of products form, right, in the standard form, this would not be allowable. This here, what's wrong in that? Right, in that particular system, what's wrong over here? Can you see that whole A, B, C, the whole thing has been barred. So this would not be possible in a standard sum of products form. Now, standard sum of products, now we we use the first alphabets of each title. So SOP, sometimes some people would call it the SOP. Okay, SOP, SOP. Yeah. So we would not allow this one. Why? Because it has got a whole thing barred. We can't allow it. All right. This is in this system. Remember, every system has its own definitions. Okay, let's now look at another system, the opposite system. Right, you guys can have a look at this example in your free time, all right? The next system is, we want to talk about is the product of sum system. Same concept, but the other way around. Product of sum. Now, what can you tell me about these two? These two are what? Odd together. What about these three? They are odd together. So we can say these two OR gates are ANDed together. So you can say AND of ORs, but it's very confusing when you say AND of ORs. So we can say what? Product of sums. Because these two sums, this sum and this sum, are ANDed together. So product of sum. Right? Or are ANDed. Another word for AND gate in this system is product. Another word for OR gate is sum. So product of sum. Once again, each OR gate is called what? A next term. Each OR gate is called a next term. All right? And each term is called a literal. Once again, literal. And what was the AND gate called in the last one? Min term. Right? So product of sum, they also call it POS. Right? POS, product of sums. This is a standard way of representing circuits in two layers. Okay. So what's the catch over here, guys? I want to introduce you to another concept now. Right. Just some rules. What's wrong with this one? Can you see that B, O, C, whole thing barred? Can you see, because this is whole thing barred, once again, just like in the last one, you can't have it as you can't have it as SOP, sum of products, because of the BO whole thing barred. So the min term is product terms in SOP, next term is sum terms in POS, right? These are similar terms, but you've got to keep track of those. Now, the whole idea, what is the whole purpose of this system? The whole purpose of this system is to reduce the circuit into two layers. The idea, why are we doing all this? Why are we doing product of sums and sum of products? The advantage of sum of products and product of sums, it may not be the minimal. Once again, it may not be the absolute minimized system. Like what we've learned, the absolute minimized system can only be done using Boolean algebra, like what we've done, right? By the way, did anyone of you attempt a tutorial, what tutorial was it? Tutorial from last week, question number 5? Has any of you attempted that? Question 5. Make sure, just note that down. Question 5 from tutorial, what tutorial was it last week? Tutorial 3, was it? Tutorial 3? Question 5. Make sure you attempt that particular problems, those particular problems, right? Because now you have all the theorems with you. You use all those 13 theorems. Now, in order to arrive at the minimum equation, right? At the most minimal equation, you use your Boolean algebra, right? Now, what does product of sum and sum of products do? It may not, once again, I repeat, it does not bring you to the absolute minimal. But what it does bring you is the least number of layers. I introduce you to another concept, the number of layers. Okay, look at this circuit. First layer, second layer. Yeah, first layer and second layer. All right. Okay, so basically, once this set of layers have done, it passes it to the second layer. Right? Okay. Sometimes some minimal equations, they may be minimum, so maybe it may be a minimum number of equations, but maybe more layers. Right? In this case, you reduce it to two-layer system. Always, sum of products and product of sums will only be two layers. So let's say if it's a sum of products, it will always start off with an AND gate and finish off with an OR gate. Two layers and game over. Two layers, right? So remember, sum of products and product of sums will only have two layers. Only have two layers. That's it. No more layers, right? That's the achievement. That is the basic achievement in sum of product and product of sums. Two layers only, and then game over after that. All right? Okay. When you come to when you talk about Boolean expression, it may not necessarily guarantee two layers. It may be extra layers, right? But sum of product and product of sums, it may be many gates, lots of gates, but the guarantee is it's fixed to two layers only. All right? Okay. Now, let's have a look at this one. This is what? What can you tell me about this? Is this sum of products or product of sums? By looking at the circuit. Look at the circuit. Product of sums, right? I know some of you may have looked at this, but by looking at this, you say, hey, it's OR gate. OR gate is a representative in this particular system. We call it like a sum, and it finishes off with a AND gate, right? Which is in this system known as a product. So it's a product of sums, right? So again, there is two layers. Can you see it's always restricted to two layers? So what product of sums and sum of product does is in hardware. Remember, my emphasis is always think of what is happening in hardware. Don't think of it like equations and tables. Think of the hardware. Always think of the hardware. All right? Okay? So in hardware, it always will be only two gates. Now the advantage is, when you think of it in terms of gates, usually when you have one gate, right? Let me show you this. Okay, that's a chip. Look at this one. This is an AND gate. Maybe I want to show you OR gate. Here, this is an OR gate. When you buy one chip, right? When you buy one chip, you don't buy. When you buy one chip, in that chip there will always be about 4 gates, 4 or 8 multiples of 4, right? Or sometimes I haven't seen 6, but generally it's about 4 gates, right? So have a look at this chip here. Let me zoom in. Or can't zoom in, right? It will always be 4 gates inside that one chip. So whilst your Boolean expression may have reduced the number of gates to just 2 gates, the cost remains the same. How? The cost remains the same because you still have to buy one chip. Whether you use only one gate, yeah, you may be using only one OR gate, but you still have to buy that one chip, and 3 gates become redundant. 3 gates in that one chip becomes redundant, right? But still you have advantage of using less energy because you're only using one gate, less complexity and all that sort of thing. Of course, yeah, things become easier, right? But the truth remains, the amount of money you spend on the chip is still the same, whether you use 2 gates or you use 1 gate. Yeah? So that is the advantage when you look at this particular circuit. How many chips will we be using for these 4 gates? Right? We'll be using just one chip, and then we'll be using a second chip for the AND gate, and therefore we end up buying 2 chips, right, in hardware. Right? Now, of course, then there is one level higher. You go into something called VHDL, which is or HDL, high definition language. So right now in your labs we are playing with chips. Like this week's lab, for those of you who will be doing it on Friday, you'll actually start playing with chips. You'll put the chip on breadboard, you'll connect things up. Okay, and maybe some of you would have done EN001, module 1, some of the tasks you deal with the actual chips. All right, now, in this particular scenario, at another level, you come to another particular thing called HDL, high definition language, which is a programming language which you learn, right, to describe this circuit. Like, for example, the programming language resembles this. So this circuit is this Boolean expression. So you code that particular Boolean expression into that language, and then your chip, it'll be one chip which will have this circuit embedded in that chip. Right? You code it, and then you place an empty chip, a blank chip, in a machine, and that machine will then program that chip with this circuit. That's at a higher level. That's how things are done in the real world, right? So at a basic level, when it's just 1 or 2 chips, and that's a very expensive exercise. The cost for that exercise is higher, but at a basic level, if you've got just a few chips, just a few OR gates, AND gates, we go and get the chip and do what you guys will be doing in the lab, right? But if it's more complex, then maybe you code it using HDL, right? Okay. All right, let's go back up to... All right, so sum of products, product of sums. Let's now have a look at this particular truth table. All right, let's have a look at this truth table. All right, for now, what I'll do is I want to, okay, I don't want to confuse you guys too much. I want to put this on Word. Okay, yes, come on. Okay, let's have a look at this truth table. Now, this truth table obviously represents a system, right? Now, the one way of how we can represent it in terms of sum of products, right? Sum of products is, what we do is we identify where the ones are, right? Because the note already has the answer, but I wanted to go through the exercise with you. You identify where the ones are located. So sum of products is a system which will always, which you can easily identify. This is one technique. I'm just giving you a technique of how to identify the sum of product equation for this table. So the question says, you are given this particular truth table for a system. It may be, let's say, a traffic light system, right? Okay. And you are required to find the sum of product equation for this. The sum of product equation. Now, this is the technique. This is the steps. Firstly, you identify where the ones are located. Where is the system giving you a 1 output? That's the step 1. Right? Where is the system giving you an output of 1? Step 2. Step 2. For each of those locations, so line number, what do we call this? We call this line number 0. Why? Because 0, 0, 0 gives you 0. 0, 0, 1 in natural binary is 1. 0, 1, 0 is line 2. 1, 1, 1 is line 7. All right, now, so what line number is this? Line 1. What can you tell me about input A? It is 0. Input B is 0. Input C is 1. So we write that out as, I hope I can write it out over here. So the sum of products equation, let us say this was Z, which is a function of A, B, C is equal to, guys, can you see my handwriting here? Okay, right. Z of A, B, and C is equal to, maybe I make the table smaller. All right, okay, now that's much better. Okay, so let's look at line number 1. What can you tell me about line number 1? There will be A bar, right? A bar and B bar and C. What's the next line? So maybe before I do this. So let's write down the equation for each of those ones. Line 1. Line 1 is equals to A bar, B bar, and C, right? Okay, what's the next one? Can you tell me where else does 1 come into play over here? Where else does 1 show up? Line 5, line 6, line 7. Right? So maybe I put this like this. Line 5. What can you tell me about line 5, guys? It's A and B bar and C. Right? Now line 6. What can you tell me about line 6? A, B, C bar. Line 7. What can you tell me about line 7? It's A, B, C. Right, in the end, the sum of products equation, will be equal to all of these guys sum of products is always and what? What do we do to all the, yeah, okay? So we put and, oh. So the sum of products equation for that particular truth table is this. That is the sum of products equation. Now, it doesn't stop there. What do we do further? We then have circuit diagram. How many layers in that circuit? There will be 2 layers. The first layer will have a bunch of AND gates, and the second layer will have an OR gate. And that's called the sum of products system, or sum of products representation of this particular truth table, whatever system it is, right? Okay, so sum of products is one way of showing your system, right? Okay, now let's talk about product of sums. Let's now talk about product of sums. Now in product of sums, what is, if somebody says represent the system shown in the truth table as a product of sums. So what do? Well, basically we identify where the output is 0. The output is 0. So line 0, line 2, line 3, line 4, right? Okay, so product of sums. So product of sums. Okay, so what lines was it, guys? Line 0. Line 0, what is the representation of line 0? A is 0, B is 0, C is 0, right? Now another way to think of it is, what you've got your three inputs, and you've got an OR gate. What do? Well, we have, show you over here. Sorry. You've got your three inputs of A, B, and C. So all we say is, what we want to represent each of these zeros. As I said in the beginning, the first step was, step 1 for product of sums, you identify where the zeros are located. Step 2, let's use some of our logic over here. What should we do? And in product of sums, what is the first layer, guys? Remember, the product of sums and sum of products is always 2 layers. The first layer would be what? Would be OR gate. Second layer would be an AND gate. So what should we do to these three inputs with an OR gate such that the output is 0? All we have to do is OR it. Okay, so line 0, it's A, O, B, O, C. You don't need to put bars there, right? Okay, now let's look at line 2. Line 2, what do we need to do to line 2 so that we get an output of 0? A, O, we need to bar the B, right? O, C. So A, O, B bar, O, C. And then line, what's the next line? Line 3. Line 3 is, what do you have for line 3? Let's have a look at line 3. A, O, B bar, O, C. You may be saying, why are we barring the B and why are we barring the C? Well, because we want to achieve an output of 0, right? We want to achieve an output of 0. So we have A, O, B bar, O, C bar, right? Now line, what's the next one? Line 4. Line 4, we have A bar, O, B, O, C. A bar, O, B, O, C. There we go. All right. So in the end, our product of sum expression, will be Z, which is a function of, again, just A, B, and C, is equal to we put these into brackets to show that those are odd together, right? And that is my product of sums expression. Okay, That is my product of sums expression. It's fairly easy. I mean, for you engineering students, this shouldn't be too much difficult. So long as you follow the steps. Just be clear that if you are doing a sum of products, what is the rules, and a product of sums. Now, okay, so let's now go back to our notes. So this was the steps and the answer. The reason why I had to go through this is because, over here it's not quite obvious of the technique. The steps are not explained. So this is the truth table. You can list out when it's 1, when the output is 1, you always show it as a product of sums. Sum of products. When the output is 0, you write it out as a product of sums. All right, now there's one more point I want to make before we leave, guys. Now, I want to show you there's another 2 expressions. So sum of products form, you can write it out as Boolean algebra as such, or you can write it out as a sum of min-term expression. All right? And basically the notation, so this is just a notation change. It's still in the sum of products form, it's only the notation is changed. Over here the notation is using Boolean algebra. Over here the notation is the sum of min-term expression. Over here product of sums is in Boolean algebra, but over here it is in sum of product of next terms expression. Right? So let me just write that out for you. Okay, all right. So for Boolean algebra, there's 2 ways. Firstly, the sum of products, or the other side is product of sums. Right? Now, the sum of products is what? It's an AND/OR system, yeah? It's an AND/OR system. What does it mean? Your first layer is AND, and your second layer is OR, right? Okay, so it's an AND/OR system. And your product of sums is a what? OR/AND system. Which means your first layer is O and your second layer is N. Now your sum of products, each AND gate is a min term, which is AND. Okay? And each of your OR gates over here is known as a next term. Now, a sum of products, you can either write it in Boolean algebra, like what we did in our exercise on the Word document, or you can write it out as a sum of min-term expression. Sum lowercase m, open bracket. Look at that. Okay? Sum lowercase m, open bracket. Right? And obviously, in order to find that, you have to identify your ones on the truth table. Now over here you have a product. Can you see the symbol change? Product of next term expressions. Right? And what do? We identify the zeros on the truth table. Right? Okay? So for example,